Hello everyone, and thanks for watching Edupedia World videos. In this video, we'll study Ampere's law, and it generally ends up making a lot of questions involving magnetic field incredibly simple. So first we saw Coulomb's law, and that was 1 by 4 pi epsilon naught q1 q2 by r squared, or just q by r squared for electric field. And then we had Gauss law, which told us integral of E dot ds is equal to q enclosed by epsilon naught. And we saw that this law, though always valid, is not always useful, because once you calculate q enclosed by epsilon naught and you equate it to E dot ds, after that there's no way you can go in most cases. But in some special cases involving symmetries, you can write E dot ds as E into 4 pi r square or E into 2 pi rl or something like that, and just take the E out, integrate the ds and calculate the value of electric field. Also, we derived Gauss law from Coulomb's law, right? I showed you how to do that. The analog of Coulomb's law for magnetic field is the Biot Savart Law, which says that the magnetic field is mu naught by 4 pi I times dl cross r by r cube. The analog of Gauss law in magnetic field is called Ampere's law, and here's how it goes. By the way, this should be over a closed loop, both of these. B dot dl is equal to mu naught times I enclosed. Right? Now the first thing I'll tell you is this is a vector, and when you start integrating vectors, you get into what is generally called vector integration, which is not in your course. So I will not show you how to derive Ampere's law from Coulomb's law, but you should believe me that it can be done. Ampere's law can be derived from Coulomb's law, and physics is pretty much the same, but the mathematics is quite complicated in this case, so we'll not get into that. Again, this is always valid but not always useful. This is useful in some special cases involving symmetries, and we'll see what kind of symmetries in a minute. Right. One more thing before that, there is one exception to Ampere's law. This is only valid if electric field through the loop is constant. Every case you'll study right now, for them this will hold true, that electric field through the loop will be constant. Later, once we reach electromagnetic induction, then we'll change the electric field in a loop and see that the magnetic field can be produced due to that as well. So I wouldn't worry about this condition right now. This condition is valid for everything we'll see right now, and later on we'll see the significance of this condition. For most of you, you probably won't even understand why this condition is needed. Right? So let's look at the first important case in which we can use Ampere's law. We have a standard straight infinitely long current carrying wire. Right. We know the magnetic field at a distance d away from it is mu naught I by 2 pi d. But we had to go through quite some mathematics to derive this. We first calculated the magnetic field due to a finite wire which subtends angle theta 1 and theta 2, and then we set theta 1 and theta 2 to be equal to 90 degrees each to calculate the field due to an infinite wire. Now for a finite wire you can't really use Ampere's law, but for an infinite wire there are lots of symmetries, right? So the first is, doing magnetic field for the past few videos, we've by now I hope understood the direction of magnetic field is given often by the right hand thumb rule. So what we'll do is, we know that if this is the current, this has to be the sense of the magnetic field. Right, it has to go like this. Larger radii, smaller radii. We're not saying that it is the same for different radii, they might be different, but for a particular radius, after a particular distance d away, the magnetic field everywhere has to have the same magnitude and the tangential direction. Right. Now what is integral B dot dl? It is what is called a line integral, and it is often also called the circulation of B. So the circulation of B is nothing but integral of B dot dl, and that is nothing but, if you go through a loop, you take this point and you calculate B dot dl for this point, that will be a scalar. Then you take B dot dl for this point, B dot dl for this point, and you just add them up. Right? So that will be integral B dot dl. If I were to keep my eyes here, then to me it would seem as though the current was coming out of the plane and this was the direction of magnetic field any distance d away. Now if we know that every point the magnetic field will be constant, because there is no reason for it not to be constant, it's completely symmetric, right? Because it's an infinitely long wire. So at every point tangentially the magnetic field will be B. Then I can replace B dot dl by B into 2 pi r, or in this case 2 pi d, because B is constant, so B will come out, and integral of dl, here dl is a scalar, see, because B dot dl is a scalar, so the integral of a scalar can't be 0, it will actually be 2 pi r. So B into 2 pi d will be the integral. That is equal to mu naught times the current enclosed in this loop. What is the current enclosed in this loop? I, right? So mu naught times I. From that we get the same result, B is equal to mu naught I by 2 pi d. So we see that using Ampere's law, very quickly we were able to calculate this result, which took quite some mathematics if we were to derive it using Biot Savart Law. A few very important points to note here. I is generally a scalar, it is not a vector, but here we have to include positive and negative currents as such. So for example, if there were I1, there was I2, and there was I3, then here it would be I1 minus I2, because first of all I3 is not enclosed within this. Just like in Gauss Law we only took the charges enclosed within the surface, but the electric field was due to all the charges. Similarly in Ampere's law the magnetic field is due to all the currents I1, I2 and I3 combined, but within the loop we'll only take I1 and I2. Also I1 is positive, I2 is negative, so it will be I1 minus I2. The important point I'm trying to stress is I1 minus I2. It could be I2 minus I1 as well if I took I2 as positive, and herein we see an intrinsic inconsistency in Ampere's law. We always have a trouble of a minus sign, which can be resolved if we take the sign on this side and this side to be consistent. So for example, if I take I1 to be positive, then this side will have I1 minus I2. Also if I1 is positive, then this, if I put my thumb, right hand thumb towards I1, my fingers would curl in the anti-clockwise direction. So the anti-clockwise direction would be the positive sense. When we talk about axis, we talk about the positive direction and the negative direction. When we talk about rotations, we talk about positive and negative senses. So the positive sense of rotation would be anti-clockwise, and because B is in the anti-clockwise direction, we'll get B into 2 pi d. Let's say we were to take I2 to be positive. That means we were to take inside the plane to be positive. Then we would get the RHS to be mu naught times I2 minus I1. But since we know that we've assumed the electric field in this direction, then the left hand side will have to be B into 2 pi d with a negative sign, right? Because if I2 is pointing away from the viewer, then this direction is positive. This is the positive sense. So if we are going in this direction, the integral will be positive. If we are going in the opposite direction, the integral will be negative. So there's an intrinsic inconsistency of a sign in Ampere's law, but that can easily be resolved provided you take the positive side to positive direction, positive sense in the case of rotation and positive direction in the case of current, to be consistent in both the LHS and RHS. If you take away from the plane to be the positive direction in the LHS, you do that in the RHS as well. If you take towards the viewer to be the positive direction, do that on both the LHS and RHS, and you should be fine. Right. So this is the first case in which we see how easy it is to calculate magnetic field due to Ampere's law. Right. By the way, something which I didn't cover in the previous video, though I should have, but we can cover it here as well, because we've just found out the electric field, the magnetic field due to Ampere's law. What will be the force between two current carrying wires? So we'll take the magnetic field due to one, we'll calculate the force on the other. These are infinitely long wires. If the distance between them is d, then due to this, the magnetic field at this point will be mu naught I2 by 2 pi d, and that will be inside the plane. What is the force on this wire due to that? It is I times L cross B. So in this case, it will be I2 times L, the length, cross the magnetic field. The magnetic field is mu naught, sorry, this is I1. I don't know why I took both I2, that's a mistake. Let's take this to be I1. So this will be I1. So this will be I2 times mu naught I1 by 2 pi d. What will be the direction? The direction of dl is upwards. The direction of magnetic field is inside the plane. So by right hand thumb rule, the force will be towards the left. But since we have taken both to be infinite wires, we can't have the length of the wire here. So generally what we describe is the force per unit length. The force per unit length F is equal to mu naught I1 I2 by 2 pi d. And if you look at the very first video of 11th class in which we talk about units and dimensions, this is how the ampere is in fact defined. If you have two wires carrying current in the same direction such that the force between them is 2 pi into 10 to the power minus 7 and the distance between them is 1 meter, then the current in each of the wires is called 1 ampere. Right? So this is the force per unit length. Also, if I2 was in the downward direction, this force would be towards the right. So parallel currents attract each other. Two wires carrying currents in the same direction will attract each other, and two wires carrying currents in the opposite direction will repel each other. This is purely due to magnetic field, because any region taken as a whole will be electrically neutral except that positive and negative charges are actually moving in it. Right. Let's take another case, and this is something we didn't see in Biot Savart Law, but now we'll see that we can actually calculate the magnetic field here quite easily due to Ampere's law. And this is a device which is called a solenoid. This is a solenoid. It's sort of like a spring, except it's a wire carrying a current I, and instead of 1, 2, 3, 4, 5, 6, 7, 8, 9 loops, there might be 9,000 loops within it. So it's actually quite dense. It would actually look something like this. Very, very dense. Right. So this is a solenoid, and we would like to calculate the magnetic field inside and outside the solenoid. So first of all, what we need to see is what the direction of magnetic field in the solenoid would be. So let's say you have a single loop. The direction of magnetic field due to a single loop is like this. It is sort of like the electric field of an electric dipole, the magnetic field of a magnetic dipole. We'll see this in detail when we study permanent magnets. Right now, I just hope you would trust me that this is the magnetic field. Right. So if we have another loop carrying current in the same sense, it would create a magnetic field. These would be like this. If we have another one, it would have a magnetic field like this. And if we look at this point, the magnetic field due to both of these loops add up. But if we look at a point like this, the magnetic field due to both these loops are in the opposite direction. Right? And the more loops you add, another one would give me another one in this direction, one in this. The more the magnetic field will be cancelled outside the loop. So if we have an infinite number of loops like this, then what would happen is all the magnetic fields inside would add up, and they would give me a constant magnetic field in the horizontal direction, and all the magnetic fields outside would cancel, and the magnetic field outside would be zero. Right? So this, I suggest you visualize it with magnetic loops once on your own, because it will be easier to understand. When you have a magnetic loop like this and a magnetic loop like this, inside the fields tend to add up, outside the fields tend to cancel. Right? So I'll draw the solenoid again, but hopefully slightly more clearer. Maybe not. So this is the solenoid, right? So now, just like in the case of Gauss Law, we took a Gaussian surface, and the whole game in applying Gauss Law to problems was to pick the correct Gaussian surface. Here we have to pick the current Amperian loop, and it will come through experience. Right now I'll just tell you that this would be a nice Amperian loop to take. Right? The magnetic field here is in this direction. So the B dot dl for these two would be 0. Magnetic field outside is 0. Right. So the net, if we take this length to be L, integral of B dot dl would be B into L. And that is equal to mu naught times the current enclosed. What is the current enclosed? If the current through the wire is L, then we'll have another quantity for the solenoid that is called L. That is called number of turns per unit length. So some solenoids might have 5 loops per meter, other solenoid might have 5,000 loops per meter, right, which would behave more like a solenoid. An ideal solenoid would have infinite loops per meter, right, or in fact an ideal solenoid would actually have a surface current moving, right. So this is the number of turns per unit length. So if we take this length, the total number of turns within this would be n into L, and the charge through one of them is I, so we'll get n into L into I. L and L will cancel, and the magnetic field is equal to mu naught Ni inside a solenoid. Right? So now we see the advantage of a solenoid. If we want a constant magnetic field within any region, all we need to do is take a wire and just apply it in loops along this, and all the magnetic fields inside it will add them up. And this is the use of a solenoid. It gives us a constant magnetic field in a constant direction. N is the number of turns per unit length, I is the current through this solenoid. Now there's another device which is called a toroid, which is easy to visualize if you think of it as a solenoid where you take one end and the other end and you join them together. So a toroid actually looks something like this. Again, there are many more loops per unit length than I'm drawing, but you get the picture. It's a solenoid except it's a complete circle. So in this, again, because there are many loops, the direction of magnetic field will be tangential inside. If this was a solenoid, it would have been like this, but I took this end and I joined them together and it became a complete circle. So in this case, B dot dl will be B into 2 pi r, where r is this radius. Outside it will be 0, this is my Amperian loop, and that will be equal to mu naught times I enclosed. Now if the current is flowing in this sense, let's say, then outside all of the currents are going in one direction and inside all of the currents are going in the other direction. So all the currents will add up as well, right? And if the total number of currents in this loops, we can talk about the total number of loops in a toroid because they'll be finite, but a solenoid, an ideal solenoid, is generally infinite, so we only talk about number of loops per unit length. But if the total number of loops is n, then n into I will be the current within this Amperian loop, and from that we get B is equal to mu naught Ni by 2 pi r. This is the magnetic field inside a toroid. Right, and solenoids and toroids are generally used precisely because they can create nice magnetic fields. A solenoid creates a magnetic field of constant magnitude in a region, and a toroid creates a circular magnetic field. Right, the magnetic field will be in this direction, and again of constant magnitude. Right. So this completes Ampere's law, and I hope by now it's clear to you how Ampere's law, even though always valid, can be used in certain situations. The three situations which we saw now were an infinite wire, a solenoid, and a toroid. Right, so in these three situations, these two we haven't done using Biot Savart Law. I haven't even tried it myself ever. Maybe it could be done, but we did this using Biot Savart Law, and we saw that it was mathematically much more complicated than using Ampere's law. Thank you.